Backseat. All right, guys, you ready to roll? I did get a couple questions over the break that I felt like I should talk to the whole class about. The first one is the easy question to answer, which is the amino acids on the picture that we talked about. They had the pKa's for the R groups, and actually the amino group and the carboxylic acid group that were part of the core structure. No, you do not have to memorize those. Okay, so generally speaking, if some of the, so I like the Lippincott figures. That's why I like to use that book, because they're so pretty and nice and colorful. But sometimes they have more detail than we're going to go into. And if there is more detail there than we really talked about, don't worry about the extra. Okay. The other question that I got, and this is, I really probably should have addressed it at the very beginning. It's a question I always get. It's a hard one to answer, which is, do we have to know the structures of the amino acids? Okay. So first of all, you have to keep in mind that all your exam questions are going to be multiple choice. Okay. So you're never going to have to draw anything out. So if that's what you're worried about, no, you're not going to have to do that. And am I going to put like a picture of isoleucine and leucine up and say, is this isoleucine or leucine or valine or something else? No, I'm not going to do that either. But if you know how they're grouped, then you already know a little bit about the structure, right? If you know they're nonpolar, then you're like, oh yeah, they've just got carbon and hydrogen. So you could look at a picture of an amino acid, and you might not know exactly which one it is, and I wouldn't necessarily ask you to tell me exactly which amino acid that is, but you could say, okay, it only has carbon and hydrogen there, so I know it's one of the nonpolar ones. That type of thing would be fair game. So the answer to whether you need to know the structure is kind of a yes and a no. I want you to be able to look at an amino acid, not necessarily tell me exactly which one it is, unless there was a particular reason that structure was very important. You wouldn't necessarily have to know what it is, but you could make some predictions on the properties. You could predict that it's going to be nonpolar, for instance. Or if it had a hydroxyl group, you could predict that, well, that could participate in phosphorylation, for example. Things like that, okay? Does that make sense to you? Okay, so that's the level of detail I want you to know. So no, don't make up 20 flashcards with the amino acid on one side and try to memorize them. That's way more detail than I want you to know, and I don't want you to, I want you to spend your time learning other things, okay? But that's a good question. If you run into any other things like that, level of detail things, let me know. And I'll let you know as much as I can. Okay, this one's actually got my both my phone number and my office location on it. Forgot to include those on the first one. And there's the lecture objectives. Once again, I'm not going to read through them. I'll let you use those to guide your studying as you wish. Okay, so in this lecture, we're going to talk about protein structure, some real basic stuff. First two lectures are pretty slow paced. Things are going to pick up as we go on in the week. So there are 4 possible levels of protein structure. The first 3 are going to be common to all proteins. Okay, unless you happen to have a particular protein that only exists as a chain, it doesn't fold up on itself, which can happen. There are some that have limited structure beyond the primary, but for most proteins, you're going to have these 3 levels of structure: primary, secondary, and tertiary. And then you also can have a 4th level of structure, quaternary structure, that applies to only proteins where you have more than one polypeptide chain. Okay, so it means we're going to have 2 or more polypeptide chains. Hemoglobin, real good example of one, and that's actually what's shown right there. It doesn't say that. That's supposed to be a picture of a hemoglobin molecule. So we're going to go through what we mean by each one of these. Final structure actually determines its biological function. So that means the proper conformation, the proper folding, the proper interactions between those is absolutely vital. You get something that causes the protein to be misfolded, like some type of mutation, or if something else that comes along that causes a protein to be misfolded, like, for example, a very high temperature, or a very low or high pH, or something like that. You're going to denature a protein. You're going to render it non-functional. Okay? So both mutations and other things that can cause misfolding are going to cause human diseases. So the amino acids are joined together by the reaction between a carboxylic acid group, carboxyl group, and the amino group of two adjacent amino acids. And that's going to happen during the process of translation, which we're going to talk about later on this week. So you have a ribosome. One of its enzymatic functions is to form that bond. So here we have a picture. We have the carboxylic acid of one group, happens to be a valine. And then we have the amino group of another amino acid, happens to be alanine. And we form that peptide bond. Okay? And that's what's shown right here in red. That's our peptide bond. Once again, the amino group and the carboxylic acid group that we're talking about when we're talking about forming a peptide bond, these are part of the core structure that are common to all the amino acids. So in this case, the R group is not participating in the formation of a peptide bond. Okay, the R group is kind of hanging off the end there. So the primary structure of a protein is simply the sequence of amino acids. That's what we mean by primary structure, just the sequence of amino acids. That particular sequence is actually going to be defined by the gene that encodes it, and we'll be talking about that this week. Okay? Proteins have a distinctive beginning and end. Okay? That means you can't just reverse it and have it be the same thing. Okay, and I'm trying to show you what I mean right here. Okay, so the beginning of a protein is always the very first amino acid in a protein sequence. It's called the amino terminus because it has a free amino group. Okay, and then at the very end, at the carboxy terminus, okay, which is the end of a protein. So the amino group is at the very beginning, the free amino group, and the free carboxylic acid is at the carboxy terminus, which is at the very end of the protein. And that's actually how they're translated. Okay, so if this protein right here was being made, the very first one amino acid by the ribosome would be arginine, and then so on as we add them. What I'm trying to tell you is, if we reverse this, and you'll notice I took the same amino acids. And by the way, here's a good example for you to practice. You could go through and actually determine, and I won't tell you what the answer is right now, but go through for practice and tell me so you can figure out what the charge is on that. Now, do it after you're comfortable with the 3-letter abbreviations. But anyway, test yourself on that. And so what I've done is I've reversed the sequence here where we started with a tryptophan and ended with an arginine, which just flip-flopped it. That's a completely different protein now. Okay, so it has a distinctive beginning and end. The carboxy terminus and the amino terminus are not equivalent. Okay, so the order that they're in is also important. Once again, the beginning is our N terminus. The end is the C terminus. Those terms, I expect you to know because we're going to use them a lot throughout the rest of the week. Okay. A few key points about the primary structure. Actually, I think the first 2 points here we've already mentioned. Primary structure is defined by the sequence of amino acids, okay, from beginning to end. It's defined by the gene. You'll see later on we can actually trim protein. We can cut pieces off. We can't really add pieces on. We can't add individual amino acids anyway. We can join polypeptides together, but we're not really going to add anything beyond what's in the gene in terms of amino acids. Now you can do post-translational modifications, which we'll talk about as well. But you can cleave parts off. Okay, so the primary structure is defined by the gene, but you can also cleave something off. It could be a little bit smaller. The amino acids are joined by peptide bonds. We already talked about that. There's your peptide bond right there. The peptide bond, okay, if we look at this peptide bond, you'll notice it does have nitrogen in it, and it does have oxygen in it. So by definition, it is a very polar bond, okay? And that's going to be important when we move on to secondary structures. So the peptide bond itself has polarity. The peptide bond itself is also rigid. So that means right around what's in this square, it can't spin. That means it's going to assume just that structure. It can't spin. Now, you're contrasting that with the R group, for example. Right here is the R group. That R group can swivel around. You can actually swivel this carbon around. Okay, so you've got a lot of possible movement there, but in the peptide bond itself, it's very rigid. Okay, that's because of the way it's very polar and it shares all these electrons, and so it can only assume one conformation. Okay, so now we have our secondary protein structure. So primary is just the sequence of amino acids. For the secondary protein structures, we're only going to consider two. Actually, the textbook includes 3 different types of secondary structures and one that's sort of fits into it. But these are the 2 big ones, okay? And so these are the 2 that I want you to know. These are the 2 that I feel are fair game for a board exam, okay? So for our purposes, there's only 2 things to consider, which are going to be the alpha helix and the beta sheet. Those are going to be our 2 secondary structures, okay? And I do want you to know what I mean by primary structure, what I mean by secondary structure. And when I say secondary structure, you should be thinking alpha helix, beta sheet. Those are the only 2 we're going to talk about. Okay, both the alpha helix and the beta sheet are made possible because of the polar nature of the peptide bond. So that's going to be the key to whether something is a secondary structure versus the next level of structures that we're going to see, tertiary and quaternary structure. The secondary structures only involve hydrogen bonding using the peptide bond in the core of the protein. Okay, so they don't really involve the R groups at all. The R groups can interfere with making a secondary structure, or vice versa. They may allow a certain section because they're smaller, for instance, or they have the appropriate charges. They may allow sections to come together, but they don't actually participate in the secondary structure. So it's kind of a little bit hard to see in this figure, but you have an oxygen on one peptide bond. So we're going to have a partial negative charge on that oxygen, right? And then you're going to have a partial positive charge on this hydrogen molecule. And so those can actually hydrogen bond with each other and actually cause the formation of an alpha helix. And what happens with the alpha helix, and you're trying to show right here, is it is a helix. Okay? And so that helical formation brings the oxygen groups and the hydrogen groups together to form that bond, and then those bonds actually stabilize the helix in that region. Okay? So alpha helix is one of the 2 big secondary structures that forms important regions of proteins. Probably by now all of you have seen those sort of stick figure drawings they do of proteins now, and they'll show you little alpha helix regions, and they'll show you beta sheet regions. Usually you can use computer programs that predict where those are going to actually happen. And so what ends up also happening is when you have an alpha helix, because you have that tight hydrogen bonding around the helix, what it does is it takes those R groups in that region and kind of points them to the outside. Okay? So depending on what kind of protein you have, you would have either very hydrophilic or very hydrophobic amino acids there, depending on whether we were in an aqueous environment or we were spanning a membrane, for example. But anyway, it's going to point them towards the outside of the molecule. Now this helix actually brings the R groups in relatively close vicinity, okay, as it spins around. So if you have a stretch of amino acids in a particular polypeptide where you have very bulky R groups, an example of a bulky R group would be tryptophan. Tryptophan has the biggest R group. Or if you have amino acids which have that are charged and they have the same polarity, like multiple negative charges or multiple positive charges, if the formation of an alpha helix would try to bring those in close proximity, those amino acids are actually going to interfere with the formation of an alpha helix. It's either a steric hindrance because it's so bulky you can't make that alpha helix, or you're bringing two like charges together and they're trying to repel each other, so it interferes with the formation. Make sense? So in some cases, you'll have a particular small region where you're going to have an alpha helix region, and then you'll have a few amino acids which are not conducive for one reason or another with that alpha helix, and you form a kink. So you can have an alpha helix and have a little kink, and then another alpha helix, or a beta sheet, or something else. So once again, you can start to get the feeling there could be all different kinds of possible protein structures. So beta sheet, that's our other major secondary structure. Once again, we're using the polar nature of the peptide bond in this case. So we're actually using both the partial negative charge on the oxygen on one peptide bond with the partial positive charge on a hydrogen on another peptide bond coming together. Okay, but in this example, what we have are strings of peptides folding back on each other. So they could potentially be a fair distance apart, where alpha helix is always right next to each other, right? It's always a region right next to each other, that tight helix. These, because they're talking about folding back, could be somewhat of a distance apart. Okay, you could potentially even have two ends of a molecule coming back and folding back and making a beta sheet. But most of the time, they're still relatively close together. But anyway, it's the same idea. In this case, we have a line drawing. You have an oxygen, which is partially negative charged. Right here you can see. And a hydrogen, which is partially positive charged, binding on each other. In this case, we're just have basically two polypeptides, or one polypeptide that's folding back on itself. Okay? Does that make sense? Can you visualize that? If you can visualize it, then you pretty much can remember it.
In order to keep them separate, could we kind of compartmentalize that the alpha sheet is with two separate polypeptides and the beta sheet is between one polypeptide?
Okay. Well, if I implied that, I misspoke. So when we're talking about the alpha helix and the beta sheet, it's still one polypeptide. With the beta sheet, you can have some separation between the stretches of amino acids that interact, whereas with the alpha helix, it's always the amino acids in the immediate vicinity of it in order to form that helix. But we're always talking about the same polypeptide chain, so ultimately it's a single polypeptide. I hope I may have misspoken and said multiple polypeptides, but it's still part of the one primary structure. It's just different ways they can fold back to make the secondary structure. One case, we're just sort of twisting a helix, so that's going to always be right next to each other. The beta sheet, they're actually kind of folding back. So you can have regions, so you have two regions of beta sheet interacting with each other. That loop that's extending could be of some variable length. They don't not necessarily right next to each other. Yes?
Would it just be the sequence of amino acids that would denote whether it would do the alpha helix rather than the beta sheet then?
Yeah, so certain amino acid configurations would actually be compatible with both. Some of them may be compatible only with one or the other. That's a level of detail we're not going to get into, and that's a level of detail that I don't know exactly how they make those predictions, other than the R groups do play a role. Certain R groups are more compatible than others with certain structures. So beyond that, they have algorithms they use in computers that are going to predict whether or not they do think they're going to have those structures, and then ultimately they have to use X-ray crystallography to see whether they actually formed that. So you guys are not going to be able to predict whether or not a region is formed. I can't predict whether or not a region is formed. I could predict that tryptophan would interfere with making an alpha helix, but I couldn't necessarily predict just off the top of my head whether a particular region was going to be one or the other. Okay? Does that make sense? Okay, so the next level of structure is tertiary protein structure. And this is the final three-dimensional structure of a single polypeptide. Okay? And the interactions that stabilize the structure, so we're getting beyond, so just remember the primary, just the sequence of amino acids. Secondary, we're only involving hydrogen bonding in the peptide bond. Now we're going to talk about things with the R groups when we're talking about tertiary, and also when we move on and talk about quaternary structure. We're talking about things involved with the R groups. So there are four main types of interactions that form this final bonding: disulfide bonds, hydrophobic interactions, hydrogen bonds, and ionic bonds. We're going to look at each of those. Disulfide bonds. We actually looked at this same figure real briefly in the last lecture. Okay, this is when you have two cysteine residues, and once again, they could be in fairly far apart on a particular polypeptide, but for whatever reason in the final three-dimensional structure, they're close to each other. You get an oxidation reaction, and you form this covalent bond. This is the only covalent bond you see beyond the peptide bond you see in the primary structure between the amino acids A protein. Because it's covalent, it's very strong, adds particular structural stability to a protein. Okay, so that's between cysteine residues. Hydrophobic interactions. So if you have non-polar amino acids, they will try to clump together and interact with each other to try to exclude water when we're in an aqueous environment, right? So here we have isoleucine and leucine. So there's a good example of a level of detail I wouldn't expect you to know. I wouldn't expect you to tell me. Actually, I couldn't have told you that. I could tell you that's a branch chain, so I knew it would be one of the three, but I couldn't have told you that was isoleucine versus leucine. So I'm never going to ask you to know levels of detail beyond what I know. Okay, so but I would expect you to look at that and say, oh, well, that's hydrophobic. And in this case, I could show you this picture without having labels, and you would say, okay, I know what that is. That's hydrophobic interactions. We have two different hydrophobic amino acids. Not sure exactly what they are. I do know they're branch chain, so I know they're one of three. But anyway, they're going to tend to bind together and exclude water. Or in the case when you have a membrane spanning domain, they can actually interact with the very hydrophobic nature of the fatty acid tails in the membrane. So they accumulate in the core of aqueous proteins. Most of the proteins we're going to talk about in biochemistry are aqueous proteins. And actually, you know, an individual nonpolar interaction, we just look at, you know, isoleucine and leucine, that's not particularly strong. But when you have a whole bunch of them in a core of a protein, that adds a lot of stability. Okay, so it can be the most significant thing holding a protein together as those hydrophobic interactions. So some proteins are really hard to denature with heat, for instance, because they have those hydrophobic interactions and they are so strong. Okay, the first two I think are the easy ones. The next two, the hydrogen bonds or the ionic bonds, if anything's going to confuse you, these are. Okay? And if I give you a picture of one of these bonds, I do expect you to be able to identify it. So I do expect you to be able to identify hydrophobic interactions or disulfide bond or ionic or hydrogen bonds. So these are the two that could confuse people. Okay, so hydrogen bonds and ionic bonds. So with a hydrogen bond, here's the crucial part. We have a partial positive charge on a hydrogen. So in this case, with hydrogen bonding, we don't have a net positive charge here. It doesn't show a plus, right? But it shares electrons unevenly. So the oxygen right there is going to be high. It's going to have a higher electronegativity. It's going to pull electrons away. Therefore, that hydrogen is going to have a partial positive charge. Okay, so partial positive charge. That's the key. So when you're looking and you're trying to figure out whether it's ionic or hydrogen, the hydrogen involved shouldn't have a net positive charge. If it has a net positive charge, it'll have a little plus there, like right there. If it doesn't have a net negative charge, or I'm sorry, net positive charge, we're talking about hydrogen bonding. So the negative charge could be a full negative charge or a partial negative charge. Okay, in this case, we have a full negative charge, but you could have that hydrogen interacting with an oxygen that's not fully negative charged. Okay, like an oxygen in a water molecule, for example, could interact with that, and that would also be hydrogen bonding. Okay? I'm belaboring this point because these are the two that are really, if anything will screw you up, it'll be these two. The other ones are simple. Once you've seen them once, you don't even really have to study them. These two are the ones that'll give you issues. So once again, the hydrogen is not fully ionized, doesn't have a full positive charge, okay, but it is sharing electrons unevenly, so it is bound, in this case, to an oxygen molecule. And then our ionic bonds, the trick here is we have R groups that are positively and negatively charged. They're actually ionized, okay, fully ionized. So we have a full negative charge and a full positive charge. That's an ionic bond, okay? Full negative charge and full positive charge. So you'll notice in this case, there's an extra hydrogen here in lysine that's going to be normally present at physiological pH, so it gives it a net positive charge. And you have, in this case, the R group of aspartate has a full negative charge. Once again, fully ionized, ionic, partial positive charge on a hydrogen is going to be hydrogen bond. Okay, so the fourth level, yes?
I don't know if this works. Oh, yeah. Can you explain the different characteristics of hydrogen bonding in the secondary structure versus the tertiary structure? Because I'm a little confused on that.
They're both hydrogen bonds, so you can have hydrogen. So the difference is now what we're talking about is hydrogen bonding between R groups. In the secondary structure, we're talking about hydrogen bonding with the peptide bond itself. So the peptide bond that's at the core of the protein, ignoring the R groups. The peptide bond that's at the core, it's polar itself. So it can actually interact with other peptide bonds, and that forms the secondary structure. In tertiary and in quaternary structure, we're talking about the R groups. Okay, does that make sense? Does that answer your question? Okay, so it's still, you can still have hydrogen bonding in both, but we're talking about hydrogen bonding in the tertiary structure between R groups. And then quaternary structure is only when you have a protein that has more than one polypeptide chain. Okay, a good example of one you're going to see, I think you're going to even see this week, is hemoglobin. Actually, we'll talk about ribosomes this week. They have a bunch of different polypeptides in there. So anything that has more than one polypeptide has quaternary structure. You can have all the same types of bonds with quaternary structure that you see in tertiary structure. I didn't list the disulfide bonds, but those could potentially happen as well. Not as common, but they can happen. In some cases, when we have a quaternary structure, we're going to have multiple copies of the same peptide. Okay, so that means you can make a peptide and then just make a whole bunch of it, and somehow that peptide joins together with the other peptides that are the same as it and makes a quaternary structure. Could have 4 of the same peptide coming together and making, and that's important for the enzymatic activity of that particular protein. Or you could have different polypeptides, okay? A real good example, and it's a good example, it's one you're going to see this week, hemoglobin. It's actually kind of an example of both of those, because in hemoglobin you actually have 2 alpha chains and 2 beta chains, okay? So it's got 2 of a particular polypeptide, but it's also got different polypeptides in there as well, so it's a good example. And the bonds that hold that quaternary structure together, once again, are going to be those hydrophobic interactions, hydrogen bonds, ionic bonds, same bonds we see in tertiary structure, okay? I believe you're also, at the same time when you talk about hemoglobin, I believe you're going to talk about myoglobin, which basically myoglobin, so hemoglobin's got 4 polypeptides and myoglobin's got 1, and you could almost think of myoglobin, and if you look at how it functions, it almost functions as a quarter of a hemoglobin molecule. Okay, both of those bind and release oxygen. That's their job. So technically those aren't really enzymes, but the binding and release of oxygen is similar to an enzymatic activity. Okay, we have a couple of diseases we're going to talk about. The first one is sickle cell anemia. Once again, all the diseases that I bring up, I don't bring them up because they're particularly fun for me to talk about. I bring them up because they're high-yield board exam diseases. Okay, this stuff you guys got to know. Anything that's going to be a real common disease is definitely going to be on your board exam. Some of the biochemical diseases, like maple syrup urine disease, are real rare, but we use all the resources to figure out which ones would actually be possibly on a board exam. But sickle cell is actually common. For genetic disease, it's actually common. Okay, and in the United States, it's actually the most common inherited blood disorder. Worldwide, there are some that are actually even more common. Thalassemia is more common. We'll talk about thalassemias later on. So what happens, well, first of all, what are the symptoms of sickle cell anemia? And one thing I want you to do, when I give you symptoms, try to associate, by the end of the story, associate why this molecular defect, and I'm going to explain to you what exactly the defect is, why that defect causes those symptoms. Okay, and hopefully I'll explain that as we go through if I didn't make it clear. But that's one, if you understand the why, you've just eliminated a lot of memorization, because then you don't have to memorize, oh, sickle cell causes episodes of pain, causes anemia, and just try to memorize that. If you know what's going on, you don't have to memorize it. It'll be logical, okay? So, and so you do have these crises, these sickle cell crises, where you get this really intense pain in certain regions, and that's where you're getting the occlusion, okay? You're getting a clot there, and that will cause pain. You get hemolytic anemia, chronic hemolytic anemia. So your body recognizes any red blood cell that's not shaped correctly and removes it from circulation. That's an example of a hemolytic anemia. And then you have increased susceptibility to infection. That's caused by all these little infarcts, all these little blood clots. That also blocks the cells which fight infection from getting to those regions. Therefore, you're more susceptible to infection. So the lifetime of a red blood cell in someone with sickle cell anemia, on average, is less than 20 days. And for a normal person, it's somewhere around 120 days. So red blood cells a typical red blood cell lasts about 3 months. And so for sickle cell, the particular mutation is you have a glutamate, which would normally be present in the normal hemoglobin, which is our HbA. So HbA in this figure, that's adult hemoglobin. Okay, HbA is an adult hemoglobin molecule. You have it replaced, a glutamate replaced by valine. Okay, and that in this figure is shown as HbS. That's the sickle cell version of It's actually the beta globin molecule. I don't know if I've got that written on the next slide or not. So it's so you have an alpha and a beta globin molecule. It's actually on the beta globin molecule. So that's our HBS right here. HBC is actually another disease, and I think Dr. Traore may talk to you about that one. Somewhat similar to sickle cell anemia. But we're not going to talk about that right now. We'll just focus on sickle cell. Okay, so this is a good chance for us to think about some of the stuff we learned in the last lecture. I know you haven't had a chance to study it yet, but glutamate and valine, those are 2 amino acids that we did talk about. Those are pretty different amino acids, right? Valine, what was valine an example of? Yeah, it's a nonpolar amino acid. And glutamate is an example of what? It's very polar. It's also charged, right? It has a negative charge. So we went from something that was nonpolar to something that's negatively charged. That's a pretty big jump. Okay, so another concept to start thinking about, and as we go through biochemistry, you'll start seeing, you get all these giant ranges of severity of diseases, or even within a same disease. You know, you'll have different severity of symptoms depending on the mutation type. In some cases, you're even talking about mutating the same amino acid, but you change it to one amino acid, you get this level of symptom. It's a different amino acid, it's higher or lower, you know, more intense. And in many cases, anyway, you can sort of logically make sense of the symptom severity by how drastic the change is. Okay, the bigger the difference in the amino acids, at least somewhat, you can predict that that's probably going to have a drastic change. So, for example, if you have valine and you just put another nonpolar amino acid, probably wouldn't be that big a deal. The nonpolar amino acids, unless it was like very different, like it was tryptophan, something much bigger or something, it's probably just going to interact the same. So you can have, if you take everybody here and you look at your hemoglobin molecules, you're going to see differences, sequence differences. You're going to see different amino acids in me versus any one of you, because there's some natural differences that don't affect the function. But when you get some, at least relatively big change, you can predict that that's going to have a severe effect. Okay, we have a little gel electrophoresis going on here. So in this case, these little slots here, they're basically loading some hemoglobin on and then subjecting it to an electric current. Overall, a hemoglobin molecule is negatively charged, so it's going to migrate towards the positive pole in this case. But in this case, we took away one of the negatively charged amino acids and replaced it by a neutral as far as charge goes. So it's going to be less negatively charged, so it's not going to migrate as fast. And that's what they're showing you. And this is actually a diagnostic test that they will actually use to diagnose sickle cell anemia. They'll actually load hemoglobin up on a gel and run that test. Now, based on that, you could probably, and since we have time, you could probably predict what's going on with HBC here. Wait, before I tell you that, I'll tell you, HBC, the mutation occurs in the exact same amino acid. Okay, so it's this glutamate's been replaced. Yeah, we changed. So what happens in that case is you actually have a positive amino acid right there. So it's even less negatively charged. Okay, but we're going to focus in on sickle cell right now. So what happens at the molecular level now? Okay, so that's a pretty minor change overall, right? I mean, you're talking about hundreds of amino acids in each one of the polypeptide chains that goes in a hemoglobin molecule. Okay, we've just changed one of those, and you get this condition. So what is going on at the molecular level? Why did that change happen? You might predict, okay, well, it's going to disrupt that tertiary structure and or quaternary structure, so maybe the protein just doesn't fold right. But as it turns out, the sickle cell hemoglobin actually, if you have enough oxygen around, it'll function fairly normally. So it's not completely non-functional. Because if it was completely non-functional, the person wouldn't be able to survive to birth, right? Or actually, with this case, because we're talking about the beta globin chain, they would survive to birth, but shortly after birth, they would die when you start making this beta globin chain. Fetal hemoglobin is a little different. So it would, because you do have adults with sickle cell hemoglobin, you know that it's got to be at least partially functional. But what happens is, so in adjacent molecules, so the replacement of that glutamate with a valine, it creates this little protrusion that you can kind of see right there, and it happens to fit into a pocket on a neighboring hemoglobin molecule, the one that's around there, okay? So we're talking about in the cytoplasm here of red blood cells. That does not normally, that interaction, that hydrophobic interaction, you don't normally see in normal hemoglobin. And actually, the only time you see it in sickle cell hemoglobin is when you have very low oxygen levels. So that's what precipitates a hemoglobin or a sickle cell crisis. Okay? And you'll talk more about this later on this week when you talk about hemoglobin. So you'll talk about there's a T form and an R form of hemoglobin. So I don't want to get too much into that right now. But anyway, what ends up happening is you create this hydrophobic interaction, and you start creating these fibers, and they become very insoluble. They actually will precipitate out, and they start getting longer and longer and longer. And when they do, they actually start distorting the shape of the red blood cell. I don't have a picture of a normal red blood cell here, but you can kind of actually, yeah, in this little capillary there, you can kind of see what a normal red blood cell looks like. Looks kind of like a donut, except in the middle, instead of having a hole, it's just got this concave part. Okay, so it doesn't actually have a hole there, but it looks like that. And it's actually very flexible. So when you get into some of the real small capillaries, it can actually kind of compress itself and squeeze through. But when you get the sickling and sickle cell anemia, what ends up happening is that fiber creates, and it actually literally looks like a sickle, right? It can't, it's not very malleable anymore, okay? So first of all, that means it can't, squeeze through some of those small capillaries that the red blood cells normally could get to. And also, so it could actually physically block them. Also, because it's sickled, it can actually interact with other cells and cause like a clot. And those are what causes the infarcts. And those infarcts are what causes the pain. Okay, and so those were some of the symptoms we were talking about right here. And because it's misshaped, you get our chronic hemolytic anemia, spleen, liver, things that are going to turn over the red blood cells. The macrophages in those tissues are going to recognize, okay, something's wrong with this cell, pull it out of circulation. So you have chronic hemolytic anemia, and once again, your cells that are going to fight infection, which we'll be talking about shortly, will not be able to reach those peripheral tissues. So when they get through those small capillaries, they're going to be blocked, therefore highly susceptible to infection. Okay? So that's a little bit of the story of sickle cell. I think when you talk about sickle cell with later on this week, you'll get more into those T and the R forms, and then you can talk about why low oxygen precipitates a sickle cell event, a sickle cell crises. The next disease we're going to talk about, we actually introduced in the last lecture, which was osteogenesis imperfecta. And just to remind you of what we talked about before, in some cases of osteogenesis imperfecta, so in the structure of normal hemoglobin, you have a glycine every third residue. And because you have that tight triple helix, it's very important in the structure in order to make it real tight. So if you substitute something else in there, it's going to interfere and make an abnormal collagen molecule. And so in some cases, I said many there, it's really, I should say some cases of osteogenesis imperfecta are caused by mutations that substitute that glycine for something else. Anything else is going to be bulkier but you can get something real bulky in there as well. That's going to disrupt the normal structure. And so the most severe forms of osteogenesis imperfecta is where you see those types of mutations, where you substitute glycine for some bulkier amino acid. Once again, this is also called brittle bone disease, and in the most severe form, death is going to occur either in utero, during childbirth, so the process of childbirth itself will break the bones in the baby. So you'll get these massive, and that's kind of what's going on here. All these bones are broken, and then you also get the bleeding that goes along with that. So now, there's actually 8 different types of osteogenesis imperfecta, but there's really 2 big board exam ones that they talk about, type 1 and type 2. And actually, they happen to be the least severe and the most severe versions. So they provide the biggest contrast, which is probably why they use that. So the type 2, which is the really bad one, okay, which is fatal in utero or in the neonatal period, usually that's caused by mutations in the collagen genes, which I just talked about, like substituting something for the glycine that's supposed to be there. Okay? Type 1 is less severe, so you can have somebody who survives and has a normal, now they're prone to breaking bones, but they still can have a relatively normal lifespan. And so what's going on there that's different than in type 2? Well, in type 1, usually what happens is we have a decreased production of certain forms of collagen. Now, we haven't talked about different types of collagen. Osteogenesis imperfecta happens to be type 1 collagen. Okay, so the symptoms you're going to see, it's because it's type 1 collagen. There's other collagen types which are going to cause, if you have mutations, they're going to cause different diseases. Okay, in this case, we're talking about type 1 collagen. What happens in type 1 collagen? We're talking about type 1 osteogenesis imperfecta. What happens in type 1 is usually you have a mutation that affects, for example, a promoter region in the gene which encodes one of the chains of this type 1 collagen. So you make normal collagen, it's just you don't make enough of it. Because you don't make enough of it, you get the symptoms of osteogenesis imperfecta in the brittle bones. And those symptoms are multiple bone fractures. So these symptoms are pretty much common to most all types of osteogenesis imperfecta. For example, there is one type that we're not going to talk about where you don't see the blue sclera. And actually, that's the one that Brick has on. He has the one where you don't have the blue sclera on the middle. If you remember, I mentioned that last lecture. But you see multiple bone fractures. That's the big thing. You see some skeletal deformities. I'll show you in a second. Blue sclera, that's one of those things that they always, every board exam review book you'll look at with osteogenesis imperfecta, they'll say blue sclera. It's a diagnostic clue. Although typically we don't like to test by putting something that makes it that obvious in there, and the board exams don't either. So they might give you a picture, and you're supposed to say, okay, well that's, and if you don't know what sclera is, that's the white of the eye. I'll show you a picture in 1 second. So you have abnormal middle ear bones can cause hearing loss, dental imperfections. So that means type 1 collagen is involved in all those tissues. I do have some pictures. Here's just one example of type 1 OI, some of the skeletal deformities you can see. Once again, I think Google Images is a really valuable tool. It's become much more valuable over the last few years. Type osteogenesis imperfecta in there and look at all the range of symptoms. You can have some types with dwarfism, for example. So there's the blue sclera, by the way. And then we have the real severe version where this probably happened during childbirth, and consequently, I believe in this case, this child is actually dead. But if not, you can see that they would not survive very long. And I also included for you guys that little study guide. Once again, there may be a little bit more information in there. We didn't talk about Creutzfeldt-Jakob disease or Alzheimer's disease. You're certainly welcome to look at those. We'll talk about those at some other point. All right, you survived. Day 1. Still 3 more of me this week. Thank you.